Welcome to the Explainer. Today, we are pulling back the curtain on the mathematical language that basically runs our entire digital world. I'm talking about everything from the movies you stream to the AI in your pocket. It's called linear algebra, and it's pretty much how computers make sense of, well, everything. So let's just start with a puzzle. Think about it. Computers are incredibly powerful, but deep down, they're just calculators. They only get numbers. So how in the world do they understand something as complex and human as your taste in music, or tell the difference between a cat and a dog in a picture? Well, it turns out they're expert translators. They take our messy, complicated, real world and translate it into a language they can understand, a structured language of data. And that language is linear algebra. Okay, so just like any language you might learn, we have to start with the nouns. These are the basic building blocks, the objects that actually hold all the information we care about. The simplest noun, the absolute most basic, is a scalar. Now, don't let the fancy name fool you. It's literally just a single number. Like the temperature outside, or your age, or the price of a cup of coffee. One single piece of data. That's it. All right, one step up from that, we've got vectors. A vector is just a list of numbers in a specific order. And this is where it starts to get really interesting, because a single vector can represent a whole concept by listing out its features. For instance, your taste in movies could be a vector, where each number is your rating for a different genre. A 9 for sci-fi, a 2 for horror, a 7 for comedy, and so on. And what happens when you stack a whole bunch of vectors together? Well, you get a matrix. It's just a grid of numbers, a 2D array. A perfect everyday example is a grayscale photo. Every number in that grid just represents the brightness of one single pixel. Or you could have a giant matrix representing the movie ratings of every single user on a streaming platform. Okay, so now we have our nouns, our scalars, vectors, and matrices. They're holding all our data. But data just sitting there isn't very useful, is it? We need to do stuff with it. We need verbs, actions that let us compare, measure, and play around with our data. Our first verb is all about size. How big is a vector? A function called a vector norm tells us its magnitude, or its length. And the most common one, the L2 norm, is probably something you already know from geometry class. It's just the good old straight line distance from the start of the vector to its tip. Okay, this is really cool. How do we compare two different vectors? Well, one way is the dot product. It tells us how much two vectors are aligned, how much they point in the same general direction. But cosine similarity, that takes it to another level. By dividing out the vector's lengths, it only looks at their direction. This is the magic behind how a recommendation engine can say your taste is super similar to someone else's, even if you've only rated 10 movies and they've rated 1,000. It's all about the direction of your taste, not the amount. Let's keep building on this, because now we're getting to the really powerful part. We're going to see how we can use matrices as these incredible transformation machines that can stretch, shrink, and rotate our data in all sorts of useful ways. Let's start with a simple but super useful action called the transpose. All you're doing here is flipping the matrix along its main diagonal. The rows become the columns, and the columns become the rows. It sounds simple, but it's a fundamental way we reorganize data to get it ready for other calculations. Now, I know what you're thinking. Matrix multiplication looks super intimidating, but the idea behind it is actually pretty straightforward. To get each number in your new matrix, you just grab a row from the first matrix, a column from the second one, and you do that dot product we just talked about. That's it. You just repeat that simple little dance for every row and every column, and that builds your final result. And all that multiplication hides a really elegant secret. It's called the determinant. It's just one single number that tells you the total effect of a matrix transformation. So if a determinant is 2, it means that matrix will double the area of whatever it transforms. If it's 0.5, it squishes it down to half the size. It's a summary of the matrix's power. Okay, now we're going from grammar to poetry. We're going beyond just moving data around, and we're starting to uncover the hidden secrets, the deep, fundamental structure that's buried inside the data itself. And that leads to this just fascinating question. When a matrix transforms space, stretching it, rotating it, squishing it, most vectors get knocked completely off their path. But are there any special vectors out there that are so fundamental they hold their ground? Vectors that only get stretched but never change their original direction? And it turns out the answer is a big yes. And these special, stubborn vectors, they're called eigenvectors. An eigenvector is that 1 in a million vector whose direction is totally unchanged by the matrix transformation. It points along a core, fundamental axis of the transformation itself. And that amount that it gets stretched or shrunk by, that little scalar value, that's called its eigenvalue. We use the Greek letter lambda to represent it. So the eigenvector gives you the stable direction, and the eigenvalue tells you just how much of a stretch or a squish happens along that direction. So here's the key takeaway, the really crucial point. While pretty much every other vector gets sent flying off in some new direction, eigenvectors show us the true spine of the transformation. They point out the directions that define what the matrix is fundamentally doing to the space. The whole process of finding these core components is called eigendecomposition. And honestly, you can think of it like finding the DNA of a matrix. You're breaking this complex thing down into its most fundamental properties, its essential directions, the eigenvectors, and the scale of its power in those directions, the eigenvalues. Now, I get it. This all might feel a little abstract. But here's the thing. This is the invisible engine that powers our world. When an AI can understand an analogy like king is to queen as man is to woman, it's because it's doing math on vectors. Every time you see a character run across the screen in a video game, that's just a bunch of matrix transformations happening in real time. And yeah, when Netflix perfectly suggests your next binge watch, it's because it found your preference vector is close to somebody else's. So I'll leave you with this final thought. Learning a bit of linear algebra isn't just about understanding how computers work. It's about learning the language that data itself speaks. So, if this is the language of data, what incredible new conversations could we have? And what new discoveries could we make if we all just became a little more fluent?